In the previous class we have discussed about regular grammars, and we have seen what are the rules for formation of regular grammars, and we have seen the definition of a regular grammar. And now in this section we are going to relate to an algorithm that is actually going to convert a given grammar into a FSM. Okay. So, we are going to relate two things, that is regular grammars and regular languages. So, regular grammars, as I told in the previous class, are going to result into regular languages. So, these regular languages are nothing but the strings that are formed from the rules of the regular grammar. So, we will go to the theorem 7.1, and it says that regular grammars define the regular languages, and the regular grammar to FSM conversion is given by a particular algorithm, which is given by grammar to FSM. So, what we give as an input to the algorithm is the grammar G, which is the regular grammar. So, what does this algorithm actually ensure? It ensures that given a regular grammar G, which consists of the 4 parts that we have studied in the previous class, where V is a set of all the alphabets, which includes both the terminals as well as the non-terminal symbols. Then sigma is the alphabet, that is what a terminal is made up of. R is set of the grammar rules, and S is the start symbol. So, these are the 4 parts of a grammar, and it assures that when we construct a machine M, so the language which is accepted by the machine M is equal to the language which is defined by the grammar. So, we are making two things equal, that is an FSM M and a grammar G. So, therefore, we look into the different steps of this algorithm. So, the first step states that we have to identify all the variables. So, V is set of all the alphabets, okay, rule alphabets we say. So, V is set of all the rule alphabets. So, we identify all V's, and create a state for each V. So, we are going to create or identify all the variables which are there in the grammar production rules, and we are going to create a new state for all the V. So, for all the non-terminals. So, we are concentrating only on the non-terminals this time. The second point states that make a state corresponding to S, and that is nothing but the start state. So, this is the second thing that we have to do. So, after identifying all the variables, we create a new state for all the different variables that are there in the production rules, and the second step that we do is we make a separate state, and that state corresponds to the S. S is nothing but the start state. So, it is regarded as the start state. Next is we have to identify the 3 kinds of productions. So, as I discussed in the previous class, so you can watch the previous video. So, we have defined what can be present in the RHS and what can be present on the LHS. So, the left hand side will always contain a non-terminal, and the right hand side can be in 3 things. Okay. So, first thing is it can either be an epsilon or it can just be a set of terminal. So, that I will call it as W, that is a single non-terminal, and then rather this is a single terminal, and then it can be in the form of some W, that is nothing but an symbol followed by a non-terminal. So, this side I am going to put some Y. So, Y goes to epsilon, or Y goes to a single terminal symbol, or y goes to a single terminal symbol followed by a non-terminal x. So, which is represented as a capital letter. So, once we have these three kinds of productions, what actions we are going to take? So, in case we have a production of this type, I will repeat it here. In case we have a production of something so in case we have a production that goes to y goes to epsilon, then we create suppose we have anything such as y goes to epsilon, then we make y as the accepting state. We make y as the accepting state. Next, for any production which is in the form of y goes to some w, so then we create a new state, we mark that state as a hash and add a transition from y to hash on w. So, this is what we are going to do. So, suppose anything is in the form of y goes to a terminal. For example, if I have something like x goes to a, then what I will do in the DFA is nothing but we will have two states, one for x that we have identified as a non-terminal. So, x will be here and then we create a new state and that state will be named as hash, and we create a transition from this state to hash over this w. So, w in this place is a, so we write a here. So, this is the rule that we are going to follow for any production which is of the type y goes to w. Then we look into another production. So, the third kind of production is nothing but y goes to some w and x. So, in this case we just add a simple transition. So, add a transition from y to x on w. So, this is the action that we are going to take. So, we just add a transition from the state y to the state x. So, both of them will be present because both of them are non-terminals on w. So, the label on the transition is going to be w. The sixth step is mark the state hash, that is the state, as accepting state, So, the next step that we are going to follow is, so after we have given all these kinds of transitions, there could be some missing transitions. So, what to do for those missing transitions? So, when we talk about missing transition, it is nothing but every state should have a transition on every input symbol. So, the grammar rules may not define all of them. So, therefore, what could be possible here is we will have a dead state, and to that dead state we are going to add all the transitions that are not present after we have finished all the 6 steps. So, therefore, for every qi on some a, so a is the input symbol and qi is a state. So, qi comma a, where such transitions are missing, add a dead state, and add the transition from Qi to D. So that dead state we are calling it as D. So from Qi to D on A. A here is the input symbol. So these are the steps that we are going to follow. So majorly we are going to follow the first 6 steps. The 7th step is quite optional, so it is not always necessary to include the dead state with all the missing transitions. So therefore we follow the 6 steps and the 7th step will always be an optional part. So now we will look into the different problems that we can solve by using this algorithm. So now we will look into the first problem. So the first problem says that strings of A's and B's ending with 4 A's. So in the previous class also we have solved the algorithm corresponding to this problem. So we have framed the grammar for this problem. So how do we frame the grammar? So first we have the start state. So if you want to write a small expression for this, a regular expression will look like A or B whole star followed by 4 A's. So any number of A's and B's chosen any number of times to this star, but it has to be followed by 4 A's. So therefore the first symbol can either be a and the second symbol can first symbol can either be a or it can be a B, and it can be more number of symbols after this A and B. So A, S. So this S can produce either A or B. Then again it is followed by a S. So this S can again produce any number of A's and B's. So any number of A's and B's. So that is nothing but A plus B whole star is actually produced by these two productions. Next we have S goes to. We should always make sure that it is followed by 4 A's. So therefore we'll write AT, then T goes to some A, Z, then Z goes to A, Y, and Y goes to A. So this is what we may write. Okay, so this is always followed by 4 A's. So if you want to know the explanation and the derivation for the same grammar, you can refer the previous video. So we have solved this. So now the aim is to convert the given grammar into the automata using the algorithm that we have studied here, which has got 7 steps. Now first of all, when we look into this grammar, okay, so how do you say that it is a regular grammar? So the grammar can be written in multiple ways, but now we are only concentrating on regular grammars. So when we look at this grammar, look at the kind of the production rule and see what is there in the LHS and see what is there on the RHS. So what is there on the LHS? On the LHS, on every production rule, you can see there is a single non-terminal. So that is what a regular grammar should have. Then next, when you look at all the RHS of the productions, it is either having a single terminal followed by a single non-terminal, or else it has got a single terminal, or else the third allowed production is something, some non-terminal goes to epsilon. So if you look at all the rules here, they follow the rules that has to be for a regular grammar. So whenever you are framing the rules, we have to stick to the ways in which we can only have the productions for regular grammar. So we'll follow the rules or the steps for conversion one by one. So identify all the non-terminals and create a state for each of the non-terminals. So we'll identify what are the different non-terminals here. Okay, so S is a non-terminal, all the capital letters are non-terminals. Okay, so S is a non-terminal. After that you have T, which is a non-terminal, and then we have a Z, which is a non-terminal, and then we have Y, which is a non-terminal. So 4 different non-terminals are there. So we have framed the 4 different non-terminals. In this, S is the start state, correct? So S is the start symbol in the grammar. Therefore, the state S which is there in the automata, it becomes the start state. Okay, so that is a step 2. So make a state corresponding to S as the start state. So we have made this state as the start state. Next, so we'll have to look for any productions which are in the form of y goes to epsilon. So we don't have any production there for y goes to epsilon. So this step we are going to skip. So then we go to the fourth step. So in the fourth step we have y goes to w. So that means y goes to w. So this is the production which we have y goes to a. So what do we do then? Then we create a new state which is hash. So create a new state and name it as hash and add a transition from y to hash on w. So here y is there. So from y you have to add a transition to hash, and what is the symbol? What is the w here? So w is nothing but a. So we write a on the transition. So that is what we do. Next, for every production which is in the form of y goes to wx, so all the rest of them are in the same format. So this is also wx, wx, wx and so on. So for all of them, what are we going to do? Add a transition from y to x. So from y to x we add a transition, okay, on w. So here we look at here. So s goes to as. So it is s to s. So s to s on what? On this a. So s to s we are going to add a. Okay. Next, again from s to s on what symbol? On b. So therefore comma I write here and write b because it is the same transition, s to s transition. Okay. So next we have s to t. So s to t, what are we adding? A. So from s to t we are going to add a. Okay. Next, t to z we are going to add a. So t to z we are going to add a. Z to y. Okay. So z to y we are going to add a. So z to y we are going to add a. Okay. So that is what we do. So from y to x, so everywhere s to s, s to s, s to t, t to z, z to y, and that is what we have done. So this is the complete transition. And the sixth step, mark the state hash as the accepting state. So we have to mark this state hash as the accepting state. So what happens here in the automata? We'll see what kind of strings are accepted here in the automata. So here you have any number of a's and b's, correct? So on the loop we have a and b, so any number of a's and b's. So before going to the final state, how many a's we are accepting? So we have to go to this state 1, 2, 3, 4th a. So 4 a's are accepted before going to the final state. So always we are making sure that the string ends with 1, 2, 3, 4, 4 a's. So this is what an automata looks like corresponding to the grammar, that is the regular grammar that we have written here. So we'll see more problems regarding this. Look into the second problem, which is strings of a's and b's of even length. So in the previous class we have solved the grammar for this. So we'll write the grammar here. So s goes to epsilon. So what is this s goes to epsilon? Because the string is of even length, the minimum length string is 0. So therefore we can have s goes to epsilon. Then after this we may generate any number of a's and any number of b's. The string can either start with a or it can start with a b. So it is not just a and b. So further we may have any number of symbols again. but we should make sure that it is of always even length. So then again T goes to AS and T goes to BS. So why we wrote T goes to AS and T goes to BS? So this T is generating the second symbol. Okay, so S is generating the first symbol, then T is actually generating the second symbol. Again if you continue with S, so again two more symbols are created. So first symbol, second symbol. Again through S we may generate the third symbol and fourth symbol. Again through S we can generate the fifth symbol and the sixth symbol. So therefore we are ending up in numbers which are 2, 4, 6, 8 and so on. So therefore we are generating even length strings. So we will see how to generate the automata for this. So in the automata, first step is identify all the non-terminals that are capital letters and you write a state for each one of them. So the capital letters are S and T. So we write S and T. What is the start symbol here? S is the start symbol. So therefore this S becomes the start state. Okay. And then you have S goes to epsilon. So if you have S goes to epsilon, then we make Y as the accepting state. So therefore S here becomes the accepting state. So when you have S goes to epsilon, that means it is able to accept empty string in the start state itself. So that is the meaning. So you have S goes to epsilon. So therefore S will also become the accepting state. Now we will go on adding the rest of the transitions which are in the form of Y goes to WX. So S goes to AT. So therefore you have to add a transition on A to T. Okay. Next S goes to B and T. So it is going to the same T itself. We write here comma B. Okay. Next T goes to AS. So from T to S we add a transition and the input symbol is nothing but the A here. Next the same thing, T to S, on the same transition we add the second symbol. What is that second symbol here? In this production it is a B. So we write here A comma B. So what is happening here? A, B, two symbols. B, A, four symbols. Then A, B, six symbols. So every time it is accepting in terms of two symbols, one from here in this transition and one from here on this transition. So two symbols are accepted every time. So this cycle can repeat any times. So therefore in terms of 2, if you repeat the cycle, so therefore it will be 2 symbols, 4 symbols, 6 symbols and 8 symbols and so on. Okay. So the odd number of symbols, that is 1, 2, 3, 4, 5. So odd numbers are actually getting rejected at the state T. So this is the end of the problem for the strings of A's and B's of even length. So we'll move on to the third problem. Okay. We'll look at strings of A's containing any number of A's. So any number of A's. So this any number of A's will also include 0 number of A's. So therefore S goes to epsilon is the first production that we can add. Then next we are aiming at producing any number of A's. So therefore I am going to write A. So S is actually producing A, but we are not limited to a single A, we want more number of A's. So which is the symbol that is generating any number of A's? S is the one which is generating A's. So therefore I am going to recursively say that S goes to AS. So what happens if you do the derivation? So if you do the derivation, if we do the derivation here, so either I can say S goes to epsilon. So this is the case where you have 0 number of A's, or else we can choose this production and say S goes to AS. From this S I can either choose epsilon and end at a single A, or I can move ahead and say I can generate more number of A's. So again this S goes to A's, again this S goes to A's. So how many number of A's have we generated here? So we have generated 3 A's. Suppose I want to stop at 3 A's. So at last this is going to be substituted for a epsilon. So here the number can be increased by recursively applying this production more number of times. So therefore this is the derivation that you can do for any number of A's, including the 0 number of A's. So now we are interested in the automata for the same grammar. So we'll see that how many different non-terminals are there in this sum. There is only one non-terminal. So therefore we write one state, that is nothing but the S. After this we identify what is the start symbol. So the start symbol is S. So this S itself will become the start state. Okay, next we'll consider the first production, S goes to epsilon. So S goes to epsilon says that S has to become the accepting state. Okay, next S goes to AS. So S to S we add a transition. So S to S we add a transition, and the symbol that we write on the transition is here. So the symbol that we write on the transition is a A. So what is this actually doing? This is S, that is the state, which is accepting any number of A's, okay, including a 0 number of A's. So that is what we have written. So the automata itself is this part of the diagram. So this is the transition diagram, that is the automata that we have written for the grammar strings of A's consisting of any number of A's. So we'll look at the fourth problem. So the fourth problem statement says that you have strings of A's consisting of at least one A. So what are we doing here actually? So in the previous problem we have looked into the solution for the grammar that generates any number of A's. So any number of A's includes a 0 also, but here they say that it's the same problem statement, but we are interested in the string that consists of at least one A. So what happens to this grammar? So this grammar was generating any number of A's, okay, including a 0, but here it says at least. So this is never possible. S goes to epsilon is never possible. So therefore S goes to epsilon will not be there. What should be there? At least one A has to be there, okay, and further you may have any number of A's which is recursively generated by this S, okay. So this is the grammar. So you can do the derivation for the same grammar, okay, based on the previous lines. So at least one A means S goes to A. More number of A's can be got by S goes to A's. Again you have S goes to A's. Again this goes to A's, and so on. You can derive any number of A's. I will say that as more number of A's. Single A and more number of A's. Okay. So you can do the derivation based on the lines of the previous derivation that we have done. So we'll write an automata for the same. Okay. So we will identify what are the different non-terminals which are there in the problem. So S is the only non-terminal. So I am going to write S as one state. What is the start symbol in the grammar? The start symbol in the grammar is S. So therefore this state S will become the start state. Okay. So next we'll look into this problem, this production rule. So S goes to A. So this is in the form of Y goes to W. So Y goes to W. So this is in the format of Y goes to W. So what are we supposed to do? We have to look into which rule? We have to look into the fourth rule of the algorithm. So you may read the fourth rule of the algorithm. So then we create a new state hash and then add the transition from Y to hash on W. So this is what we are going to do. So we are going to create a state and we'll call this hash. We will add a transition from S to hash as, what is this? A, the symbol is A, so that is nothing but A here. Also S goes to AS, we will consider the second one. So S to S we are going to add A. Okay. So since we have obtained the hash, okay, since we have obtained the hash, so mark the state hash as the accepting state. So this sixth step will come into picture. So therefore we will mark this state hash as the final state. So what are we doing here? So before going to the final state, there has to be a single A. So that means we are making sure that at least one A is there before we go to the final state. If you wish, you can have more number of A's before going to the final state. Okay. So this is the automata that we write for the grammar. So we will look into the fifth problem. Obtain grammar to generate strings of A's which are multiples of 3, strings of A's which are multiples of 3. So therefore, what are we trying to do here? So if you have A's, there always have to be in multiples of 3. So that means either 3 A's have to be there, or else 6 A's have to be there, or else you should have 9 A's, okay, and then the rest of the multiples of 3 have to be there, okay. So this is how the string should look like. So now we are going to generate a regular grammar for this, okay. So when we generate a regular grammar, so first thing what we do, S goes to, will generate the first A. So we have generated the first A. So this is not the end of it, we need the second A. So the minimum string here is 3, okay. So we take 3 A's as the minimum string. Then the same 3 A's have to be repeated n number of times to get the multiples of 3. So first A is generated and then we write a variable here. So this A is going to be generating the second A. So A goes to, so this has generated the second A. Then I write B here. Then B has generated the third A, okay. Next, 3 A's are over, again the same cycle has to repeat from S, okay. So again if I repeat the cycle from S, again 3 more A's will be repeated. So therefore the variable that I am going to add here is a S, okay. So this is how you write the grammar. And suppose that we just need 3 A's, we don't want the second cycle, that is we don't want 6 A's or 9 A's and so on. So what do we do? So S has to end somewhere, so S goes to epsilon. So if you try to derive this, you will get A's in terms of 3's, okay. So we will write a automata for this. So we will identify what are the different variables which are there here. So S, A, B are the different variables. So we will write 3 states. So first we will write 3 states. So that's S, and then we will write A, okay, and then we will write B. So S, A, B, okay. What is the start state? S is the start state. So S will become the start state because S is the start symbol in the grammar, okay. Next, A and capital A. So therefore 2A, I write a A, then A to B, A to B on A. So A to B on A. Next, B to S on A. So B to S, B to S on A, B to S on A, okay. Next, S goes to epsilon. So S will become the final state, okay. So I think in the previous classes we have done similar problem, okay. So where we have the string length which is multiple of 3. So whenever you take any number that is nothing but the length of the string, mod 3 it has to be equal to 0. Okay. So, we are interested in anything, any number that is the length of the string, mod 3 equal to 0. So, what happens here? So, we will take a string which is w is equal to a. So, starting from here, so a, second a, and then you have the third a. So, accepted here. So, what if we have the length of string is equal to 0. So, how much is 0 mod 3? So, 0 mod 3 is equal to 0. So, therefore, we are interested in epsilon also. So, epsilon also will be taken up or accepted here at S. Next, in case this length w is equal to 3, how much is 3 mod 3, which is equal to 0. So, 1, 2, 3 accepted here at S. Okay. So, what if the length of the w is 6? So, 6 mod 3 is equal to 0. So, 1, 2, 3, 4, 5, 6 will be accepted. Okay. So, any length of w, okay, in terms of 3 has to be, when you divide it by 3, the remainder has to become 0. So, all such strings will be accepted in this automata. So, next we look at the sixth problem. Obtain a grammar to generate strings of A's and B's, strings of A's and B's with any number of, with at least one A, at least one A. Okay. So, this is a problem statement. We have to obtain a grammar to generate strings of A's and B's with at least one A. So, they do not place a constraint on how many A's and B's are there altogether. Okay. There can be any number of A's and B's, but that string should have at least one A. So, therefore, the minimum string here is S goes to A. So, we are not bothered about the A's and B's here, it should have at least one A. So, therefore, we have S goes to A. There can be 0 number of B's and 0 number of A's, apart from this at least one A. Okay. So, therefore, this is the first production that we can write. Then we will frame the next production. So, the next production aim is to generate any number of A's and B's. So, there has to be more number of A's and more number of B's. So, S goes to, recursively I write AS. So, what is happening here? Any number of A's are getting produced. Then again we write S goes to BS. So, any number of B's are produced. We are not bothered about the order also, because whenever I substitute for this S, I can either choose the second symbol as A or I can choose the second symbol as B. Again, when I choose the production rule for S, the third symbol again has a choice between A and B. So, the order does not matter here. Okay. So, these are the productions that we are going to write for the grammar statement. So, these two are producing any number of A's and B's, but this is always making sure that there is at least one A. Okay. So, next, how do we write the grammar rule for this? Okay. So, here we have only one non-terminal. So, therefore, S, start symbol is S, therefore, start state is S. We will consider the productions now one by one. So, this is again in the form of Y goes to W. So, this production is in the form of this. So, rule 4 will apply. Okay. So, what we do here is we generate hash, okay, and we will add a transition from S to hash on this symbol. Okay. So, we write A here. Next, S goes to AS. So, S to S, A. S goes to BS, S to S, B, comma B. Okay. Also, since this state has come into picture, sixth rule will also apply. We will write here as we will make that as the final state. So, what are we doing here? We have any number of A's and B's, but the string should have at least one A before it goes to the final state. So, this is the solution for the grammar that we have written here. So, this is the automata produced for this grammar. So, for each of the grammar that we have written, you may have more than one derivation. So, you try to perform more than one derivations for each one of them and try to frame the strings, and also make sure that, or you can also verify that the strings that are getting produced by the grammar will always belong to the language. Also, the aim of the grammar is the language which is accepted by the machine should be equivalent to the language of the grammar. So, whatever strings this grammar is producing, those strings has to be accepted by the automata also. So, the language of the automata and the language of the grammar are both equal, they are same. So, this is what the concept of regular grammars and regular languages is. Thank you.